resume the comparison that we made just now, and imagine beings without thickness living on one of these surfaces, they will regard as possible the motion of a figure all the lines of which remain of a constant length. Such a movement would appear absurd, on the other hand, to animals without thickness living on a surface of variable curvature. These surfaces of constant curvature are of two kinds. The curvature of some is positive, and they may be deformed so as to be applied to a sphere. The geometry of these surfaces is therefore reduced to spherical geometry, namely Riemann's. The curvature of others is negative. Beltrami has shown that the geometry of these surfaces is identical with that of Lobachevsky. Thus, the two-dimensional geometries of Riemann and Lobachevsky are connected with Euclidean geometry. Interpretation of non-Euclidean geometries. Thus vanishes the objection so far as two-dimensional geometries are concerned. It would be easy to extend Beltrami's reasoning to three-dimensional geometries, and minds which do not recoil before space of 4 dimensions will see no difficulty in it, but such minds are few in number. I prefer then to proceed otherwise. Let us consider a certain plane, which I shall call the fundamental plane, and let us construct a kind of dictionary, by making a double series of terms written in 2 columns, and corresponding each to each, just as in ordinary dictionaries the words in 2 languages which have the same signification correspond to one another. Space, the portion of space situated above the fundamental plane. Plane, sphere cutting orthogonally the fundamental plane. Line, circle cutting orthogonally the fundamental plane. Sphere, sphere, circle, circle, angle, angle, distance between 2 points, logarithm of the anharmonic ratio of these 2 points and of the intersection of the fundamental plane with the circle passing through these 2 points and cutting it orthogonally, etc. Let us now take Lobachevsky's theorems and translate them by the aid of this dictionary, as we would translate a German text with the aid of a German-French dictionary. We shall then obtain the theorems of ordinary geometry. For instance, Lobachevsky's theorem: the sum of the angles of a triangle is less than 2 right angles, may be translated thus: if a curvilinear triangle has for its sides arcs of circles which, if produced, would cut orthogonally the fundamental plane, the sum of the angles of this curvilinear triangle will be less than 2 right angles. Thus, however far the consequences of Lobachevsky's hypotheses are carried, they will never lead to a contradiction. In fact, if 2 of Lobachevsky's theorems were contradictory, the translations of these 2 theorems made by the aid of our dictionary would be contradictory also. But these translations are theorems of ordinary geometry, and no one doubts that ordinary geometry is exempt from contradiction. Whence is the certainty derived, and how far is it justified? That is a question upon which I cannot enter here, but it is a very interesting question, and I think not insoluble. Nothing, therefore, is left of the objection I formulated above. But this is not all. Lobachevsky's geometry being susceptible of a concrete interpretation, ceases to be a useless logical exercise, and may be applied. I have no time here to deal with these applications, nor with what Herr Klein and myself have done by using them in the integration of linear equations. Further, this interpretation is not unique, and several dictionaries may be constructed analogous to that above, which will enable us, by a simple translation, to convert Lobachevsky's theorems into the theorems of ordinary geometry. Implicit axioms. Are the axioms implicitly enunciated in our textbooks the only foundation of geometry? We may be assured of the contrary when we see that, when they are abandoned one after another, there are still left standing some propositions which are common to the geometries of Euclid, Lobachevsky, and Riemann. these propositions must be based on premises that geometers admit without enunciation. It is interesting to try and extract them from the classical proofs. John Stuart Mill asserted that every definition contains an axiom, because by defining we implicitly affirm the existence of the object defined. That is going rather too far. It is but rarely in mathematics that a definition is given without following it up by the proof of the existence of the object defined, and when this is not done, it is generally because the reader can easily supply it. And it must not be forgotten that the word existence has not the same meaning when it refers to a mathematical entity as when it refers to a material object. A mathematical entity exists provided there is no contradiction implied in its definition, either in itself or with the propositions previously admitted. But if the observation of John Stuart Mill cannot be applied to all definitions, it is none the less true for some of them. A plane is sometimes defined in the following manner. The plane is a surface such that the line which joins any two points upon it lies wholly on that surface. Now, there is obviously a new axiom concealed in this definition. It is true we might change it, and that would be preferable, but then we should have to enunciate the axiom explicitly. Other definitions may give rise to no less important reflections, such as, for example, that of the equality of two figures. Two figures are equal when they can be superposed. To superpose them, one of them must be displaced until it coincides with the other. But how must it be displaced? If we ask that question, no doubt we should be told that it ought to be done without deforming it, and as an invariable solid is displaced. The vicious circle would then be evident. As a matter of fact, this definition defines nothing. It has no meaning to a being living in a world in which there are only fluids. If it seems clear to us, it is because we are accustomed to the properties of natural solids which do not much differ from those of the ideal solids, all of whose dimensions are invariable. However, imperfect as it may be, this definition implies an axiom. The possibility of the motion of an invariable figure is not a self-evident truth. At least, it is only so in the application to Euclid's postulate, and not as an analytical a priori intuition would be. Moreover, when we study the definitions and the proofs of geometry, we see that we are compelled to admit without proof not only the possibility of this motion, but also some of its properties. This first arises in the definition of the straight line. Many defective definitions have been given, but the true one is that which is understood in all the proofs in which the straight line intervenes. It may happen that the motion of an invariable figure may be such that all the points of a line belonging to the figure are motionless, while all the points situated outside that line are in motion. Such a line would be called a straight line. We have deliberately, in this enunciation, separated the definition from the axiom which it implies. Many proofs, such as those of the cases of the equality of triangles, of the possibility of drawing a perpendicular from a point to a straight line, assume propositions the enunciations of which are dispensed with, for they necessarily imply that it is possible to move a figure in space in a certain way. The fourth geometry. Among these explicit axioms, there is one which seems to me to deserve some attention, because when we abandon it, we can construct a fourth geometry, as coherent as those of Euclid, Lobachevsky, and Riemann. To prove that we can always draw a perpendicular at a point A to a straight line AB, we consider a straight line AC movable about the point A, and initially identical with the fixed straight line AB. We then can make it turn about the point A until it lies in AB produced. Thus we assume two propositions: first, that such a rotation is possible, and then that it may continue until the two lines lie the one in the other produced. If the first point is conceded and the second rejected, we are led to a series of theorems even stranger than those of Lobachevsky.